Hello students, good morning. Today we will discuss about the moving coil galvanometer. In the chapter current electricity, already we have discussed about the moving coil galvanometer. But in that chapter we have discussed how to convert the galvanometer into ammeter or into voltmeter. So here we already know that the galvanometer is a device which is used to measure the current. But ammeter also a device which is used to measure the current. Then what is difference between ammeter and the galvanometer? Ammeter can measure the current, large current, that is the current in ampere. But galvanometer can measure a small current or very small current which is in milliampere or in microampere. Instead of ammeter or voltmeter, if you use the galvanometer directly, then it may be damaged due to the excess current. Therefore, we must have to convert the galvanometer into ammeter, and that how to convert it we have already discussed in the chapter current electricity. Then now we will today discuss about the galvanometer, how galvanometer is constructed. There are the suspended type galvanometer and the pivoted type galvanometer. Here suspended type galvanometer is shown. Now what is the principle of galvanometer? The principle, the torque exerted by a magnetic field on a current carrying coil. In last lecture we have discussed about the torque exerted by the magnetic field on a current carrying coil, and that principle is used to construct the galvanometer. That in last lecture we have discussed what is mean of torque and how this torque rotates the coil, and when the coil is placed in magnetic field and current is flowing through the coil. Now the coil have the number of turns here. There are the n number of turns, and the strong magnetic field is applied here. N pole and S pole are shown here, and between these two poles the coil of number of turns is situated. Here the upper suspension is given to this coil and lower suspension, that is spring, is given here. In between this number of turns or this number of turns there is a iron core in between this number of turns. Iron core is used, or soft iron core is used here. Why we use the soft iron core for this galvanometer? Because we know that in magnetism chapter we discussed that there are the three types of material, that is diamagnetic material, paramagnetic material and ferromagnetic material. Diamagnetic materials are the materials which opposes the magnetic field or they does not accept the magnetic field. Then paramagnetic materials, they accept the magnetic field, but ferromagnetic substance which strongly accept the magnetic field, and we know that the iron is the ferromagnetic substance, and this iron core is used here because it accepts the strong magnetic field, and here we need the strong magnetic field, and susceptibility of the ferromagnetic substance is also the large. Therefore the soft iron core we have used here for the strong magnetic field, and here the coil is used, and the mirror is used here to observe the deflection in the coil when this coil rotates due to the torque. In last lecture we have already discussed that the coil is placed in the magnetic field, and if there are the number of turns for the coils and I is the current passing through the coil, then the torque produces in the coil due to the magnetic field, and this torque rotates the coil. This torque rotates the coil, and the rotation produces in the coil. Now, suppose I is the current which is in this direction here. We can show the direction of current here. We have already discussed that how to find the force exerted due to the magnetic field. Here on this line and this another line, these two forces are responsible for the rotation of the magnetic field. Now, this is the plane of the coil. This is the plane of coil, and the direction of magnetic field is from N pole to S pole. This is the direction of magnetic field, and this is the plane of the coil. Plane of the coil and the magnetic field are in parallel. Plane of coil and magnetic field are parallel. But when we take the area of this coil, then the area, how to take the area of this coil, we can observe this or find out by, suppose this is the area or surface, plane surface of the coil. Then here are the number of turns around the iron core. Here is, suppose there is a iron core, and the number of turns are around this iron core. Then this is the plane of the coil, and this is the magnetic field in this direction from S to N. Therefore, the plane and magnetic field are parallel to each other. But we have to find out the surface area or area vector of the coil. Then area vector is always perpendicular to the plane. This is the plane of coil. And suppose this is the area vector. This area vector is perpendicular. We take the area vector always perpendicular to the plane of the coil. Therefore, we can say that the magnetic field is in this direction. This is the direction of magnetic field, and this is the direction of area vector. Therefore, we can say that the area vector is perpendicular to the direction of magnetic field. This is the direction of magnetic field, and this is the direction of area vector. Therefore, this is perpendicular to the direction of magnetic field. And this coil rotates. How this coil rotates? Yesterday we have discussed that the one force is acting in this direction, and then another force is acting in this direction. These two forces acts on a coil, and this coil due to these two forces start to rotate at this time. And as the current passing through this coil increases, as the current passing through this coil increases, the torque also increases, because we know that the torque is equal to N I A B sin theta. We have already discussed the torque is equal to N I A B sin theta. N is the number of turns given here. Then I is the current passing through this coil. A is the area of coil, and B is the magnetic field, and the theta is the angle between the area vector and the magnetic field. Now, the torque is equal to NIAB sin theta. Here, number of turns are constant. If number of turns are constant, area is remains same, magnetic field also constant. Then the current, if the current through the coil maybe changes as the current increases. As the current increases, then the deflection in the coil also increases, and therefore the torque also increases. That is, we can say that the torque is depend upon the current passing through the coil if other quantities are remains unchanged. Now, if we take the theta is equal to 90, because the theta is the angle between area vector and the magnetic field. This is the magnetic field, direction of magnetic field, and this is the direction of area vector. Therefore, these two quantities are perpendicular to each other. Therefore, you can take the theta is equal to 90 degree. Then the torque will be equal to NIAB, because you know that sin 90 is equal to 1. Sin 90 is equal to 1. Therefore, torque is equal to NIAB. And this torque is responsible for the deflection of coil. Therefore, this torque can be written as tau inverse D is equal to NIAB. Now, when current passes through this coil and the magnetic field is perpendicular to the area vector, then this coil start to rotate. As the current increases, then coil start to rotate at this time. And when the coil rotates, then the restoring force is produced in the coil. The restoring force produces in the coil because there is a twist for this coil. When this coil rotates, the lower suspension given here, there is a twist in this coil, and due to the twist in this coil, as this coil rotates, this coil also twisted, and therefore due to the twist in this coil, the restoring force is produced in the coil. And this restoring force is responsible to regain the original position of the coil when the current passes through the coil is stopped. As the current passes through coil is stopped, then this restoring force regains the coil to its original position. And therefore, we can say that the restoring force is directly proportional to the angle, that is a restoring force the coil rotates, the restoring force produces in the coil, which brings the coil to its original position. As the current increases, then deflection in the coil also increases. That is, as current increases, this is the original position. As current increases, deflection in the coil also increases, and the deflection is denoted by the phi. When the restoring force balances, or restoring torque balances the torque applied by the magnetic field. Restoring torque balances to the torque applied by the magnetic field. Then this coil stops rotating, and the current I, or steady current will pass through the coil. And this restoring torque is directly proportional to the deflection. Here we can say the deflection in coil. Therefore, restoring torque can be given by this involved tau inverse R, directly proportional to the phi, and therefore we can write here torque is equal to K into phi. And we know that the restoring torque is equal to the deflecting torque. Restoring torque is equal to deflecting torque. Therefore, we can write here D. So D is equal to R. Therefore, put the value of deflecting torque, that is NIAB, is equal to the value of restoring torque is K. Therefore, we can find the formula of I by using this equation. That is, we can write here I is equal to I is equal to K into phi upon NAB. Or also we can find the angle, that is phi is equal to INAB upon K. Okay. The phi is equal to, phi is the angle of deflection, and we can write this equation as NAB upon K into R. Here K, this K is the twist constant of the coil. This K is twist constant of the coil, and that depends upon the material which is used here. The value of K is depends upon the material that is used here in the coil. Now, from this equation, we can say that if number of turns are unchanged, area of the coil is remain same, magnetic field will remain same, then the twist constant is also constant, remains unchanged, then the phi is directly proportional to the current. That is, the deflection in the coil is directly proportional to the current. We can write here the deflection in the coil is directly proportional to the current if other quantities are remains unchanged. By using this equation, we can find out the current in the coil. That is, as the current increases in the coil, then deflection also increases. And by using this, the pointer is given in the galvanometer, and that pointer is used to find the current in the galvanometer or current passing through the galvanometer. Okay. Here another galvanometer figure is shown here. Two magnetic pole, N pole and S pole are shown. Iron core is shown here, and this is the pointer is shown, or a coil is given here, and this is the radial magnetic field is used here. The magnetic line of force will be in this type. Therefore, these are the radial magnetic field, and this is one type of galvanometer, and this is the other type of galvanometer. Okay, we know the magnetic dipole moment is given by equation mu is equal to NIA. the magnetic dipole moment, that is mu is equal to Nia, where N is the number of turns, I is the current and A is the area. Now we always denote the unit vector which is used to indicate the direction, and here unit vector is used to indicate the direction of magnetic movement, magnetic dipole moment. Therefore, and also we know that the torque is equal to N I A B sin theta. Torque is equal to N I A B sin theta, where N is the number of turns in the coil, I is the current passing through the coil, A is the area of coil, B is the magnetic field, and theta is the angle between the area vector and the magnetic field. Now we know the magnetic dipole moment is equal to mu is equal to Nia. Therefore, instead of Nia we can put here, therefore torque is equal to mu into B sin theta. Here in this case, this magnetic moment mu is equal to the magnetic moment and B is the magnetic field, and here theta is the angle between the magnetic moment and the magnetic field. Here theta is the angle between area and magnetic field. In this case, we can say that the theta is the angle between magnetic moment and the magnetic field. How can you find out the direction of magnetic movement? Or we can say the theta is the angle between the direction of magnetic movement and the magnetic field. But how can you find the direction of magnetic movement? Now suppose this is the coil, this is coil, this is the direction in the direction of current in the coil. Now we can say you are using the right hand, the fingers, take the fingers in the direction of current. Place the right hands, these fingers in the direction of current, and then this thumb will indicate the direction of magnetic movement. Therefore, this will be the direction of magnetic movement. Therefore, we can say the direction of magnetic movement and the direction of area vector is the same. Therefore, we can take any of this, that theta we can take as the angle between A and B, or we can take the theta as the angle between the direction of magnetic movement and the magnetic field. By using this, we can write the torque is equal to mu cross B. This torque will be equal to, in vector form, the torque, vector torque is equal to vector mu cross vector B. Now, in electric field, torque in electric dipole, torque in electric dipole is the torque is equal to this momentum into electric field. Say this equation 1, this equation 2. The torque is equal to P is the momentum in electric field and E is the electric field. Therefore, we can compare these two equations, the torque in magnetic field and the torque in electric field. Okay. Now we will discuss about the magnetic potential energy. We know that the electrical potential energy is associated with the electric dipole, and the potential energy of electric dipole movement P in the electric field E is given by the equation U is equal to minus P dot E. P dot E. The potential energy or electrical potential energy is given by equation minus P dot E, because the potential energy is associated to the electric dipole. Therefore, we can say that U is equal to minus P dot E. Now, magnetic potential energy. This is the electric potential energy in electric field. Equation 1. Then magnetic potential energy in magnetic field is, that is, we can say that the U is equal to minus U dot B, minus U dot B. Here potential energy is the scalar quantity, therefore this is the dot product of two vectors. This is also the potential energy in magnetic field, scalar quantity, therefore this is also the dot product. Therefore we can write this equation. The dot product of two vectors is given by U B cos theta, and theta is the angle between mu and B, that is magnetic dipole moment and the magnetic field. Now we can consider here theta is the angle between and B. In this case, if you take the theta, suppose this is the case first, theta is equal to, the theta is equal to 0. If you take the theta is equal to 0, then the U is equal to minus UB cos 0. And we know that cos 0 is equal to 1. Since cos 0 is equal to 1, therefore mu is equal to U is equal to mu into B. Cos 0 is equal to 1. Theta is the angle between mu and B, that is, and theta is equal to 0, that is, the magnetic movement and the magnetic field are in the same direction. Then the energy of the dipole will be maximum, that is, will be equal to minus mu into B. And then we can case second, that is, if the theta is equal to 180 degree, theta is equal to 180 degree, then we can write here U is equal to mu into P cos theta. This is the dot product. Energy is equal to mu dot B. This is the dot product. Therefore, we here taken as cos theta, that is magnitude of energy, is given by this equation, and this theta is equal to 180 degree. Therefore, we can write 180 instead of theta. Therefore, here will be minus mu b cos 180. Therefore, we know that cos 180 is equal to minus 1. Therefore, we can write here u is equal to this minus will cancel, and this will be u is equal to mu into mu. Therefore, this is the magnetic dipole in the magnetic field. When the magnetic moment and the magnetic field are anti-parallel to each other. Here in this case, when the magnetic moment and magnetic field are parallel to each other, then we can say by this figure we can show this. Suppose this is the direction of magnetic field, magnetic moment. This is the direction of magnetic field, and these are parallel to each other. That is, theta is equal to 0. And if this is the direction of magnetic moment, and this is the direction of magnetic field, that is, theta is equal to 180 degree or anti-parallel to each other in 180 degree in this case, and theta is equal to 0 in this case.